Okay, thank you all for joining us. Uh, you are in Global Flood Cross-Cutting Project monthly meeting, and as the first Friday of every month, we have this monthly meeting with our keynote speakers, and we discuss about how we are going to move on with this initiative. So thank you again for joining us. Just a brief summary of this initiative. We started this idea sometime in 2023 by GEWEX director Peter pushed this initiative. I'm glad he did it. And then we started first by conducting a workshop to understand the global challenges associated with the flood modeling and process understanding. And then after the workshop, we submitted a proposal to the GEWEX, and it got accepted and approved as a GEWEX crosscut project. And then we started in 2025 officially working on this proposal and on this initiative. So we also would be very thankful if you guys could contribute to our report, because after we've done with the monthly meeting, we will work on this report and submit it to GEWEX. So basically, we are going to synthesize all the data we have, all the studies across the world about flood related research, from process understanding, from modeling, from risk assessment, going to climate change impact on the flooding, and then the management, adaptations, and also how the future projection may look like. So if you are interested to be part of this report, please include your publications here. So we would be including your results and the outcome of your paper or your publications there, and then we invite you to contribute to this report. All right. So today for February meeting, we have Professor Conrad Wasko from the University of Sydney as our keynote speaker. Conrad is also part of the Global Flood Cross-Cutting Project team, and we are glad to have him and his contribution to this initiative. So, Conrad, are you ready to start?
Yes, I'll share my screen.
Sure. Yep. Thank you all.
Okay, hopefully you can see my slides. Shout out if you can't. Look, I've chosen to talk about modeling extreme rainfall for a couple of reasons. One is that even though for pluvial flooding, we rainfall isn't a sufficient, I guess, isn't sufficient for flooding. I mean, you need other conditions, sometimes like wet soil. It is necessary, I guess, if you're going to get pluvial flooding. So I hope we're happy to accept that looking at changes in extreme rainfall due to climate change is a very relevant topic to flooding. The other reason why I wanted to present this is because in this presentation, I can really give a truly Australian context. Because I'll go through my students' PhD journey on modeling extreme rainfall changes. The other part of this is that as part of understanding flooding, modeling flooding, in the engineering context, we do design flood estimation using IDF curves. And for those, we need to know how extreme rainfalls are changing and all different rarities, from frequent to rare events, you know, 1 in 2 to 100 events, for example, and up to the PMP. And the other part of that is that you also have to look at different durations. So there's a lot of things to look at. So with that context in mind, we posed the PhD problem through what are our lines of evidence for extreme rainfall changes? And you can contest that there might be others, but we grouped them into 3 historical trends. So we can look at how our observations have changed. And this is from the point of view that if you have historical observations, you would implicitly feel confident that those observations have probably captured all the processes that are changing with climate change. But you can't really project historical trends necessarily with any confidence. I mean, indeed, it's just often a linear trend, and we don't know if the future changes will follow the same path. So Lan and Jayaweera did looked at the historical trends and published 2 manuscripts. And there's another line of evidence, which is correlations. You can look at, say, maybe how extreme rainfall is coincident with temperature and look at that correlation, or you can use, in non-stationary models, you can use covariates such as temperature. That's another type of correlation. So that's what she did. She used non-stationary GEV models to look at how extreme rainfalls are changing. And the final line of evidence really modeling, and I think this is our strongest line of evidence, the reality being that incorporates all the physics. Well, maybe not all the physics. That's, again, depends on how you're modeling. But look, and the main thing here is that when we want to know how rainfall is changing into the future, and if we want to know that, then we need to be modeling the future. And really, our primary line of evidence for modeling the future is indeed climate models. And there is issues there that maybe not all the physical processes are represented. So each sort of line of evidence has pros and cons. And so this is very much in the Australian context. We looked at all these lines of evidence to see what they could tell us about the impact of climate change on extreme rainfall. But I'd like to think that hopefully this will resonate with your experiences as well. So to start off our data set, we're quite fortunate in Australia that there's a lot of sub-daily rainfall records, and these are the ones that we picked. It was just under 40 stations across Australia. These were picked because they had relatively long record lengths. It was 54 years, I think, in the end at each of these sites of 6-minute resolution. You can see that on the left-hand side, I've got the I think it's the SREX regions, the IPCC, on the right, the Köppen climate zones. You can see that we're covering all the climates really that exist in Australia, from the real arid in the centre to more tropical in the north and temperate in the southeast. So we've got a reasonable spread of the climates with these gauge stations. So as any trend test would start, I think we can pick annual maxima, so 6-minute annual maxima, and we can fit a Mann-Kendall trend test to that data. I would argue that this presents very strong evidence, this figure, that 6-minute annual maximum rainfall have been historically increasing across Australia. You can see the arrows point up, indicating an increasing trend. The p-values are significant. However, when we look at 1-day rainfall, so these longer durations, there is very little or essentially no evidence of any change increasing or decreasing. And we can also fit a sand slope to each of these stations, to the annual maximum. And we can aggregate all those trends and across all those stations as a box plot. So that's what I'll show next. And for all the durations that we aggregated for, up to 7. So as I presented before, the 6-minute rainfalls are increasing historically across Australia. So we can see that on the left-hand side here. But really, once we start getting to longer durations, just longer than an hour even, there's not really any trend, positive or negative, on average across Australia for our annual maximum. Now, the thing is that annual maxima are not particularly rare, particularly if we're talking about something like flooding. So we want to look at rare events and how they're changing. And we have 2 ways of doing that. We can split the sample. So in this case, on 1995, fit a GEV to the start on the first half, also a GEV to the second half, and compare the difference between those fitted GEVs for rarer quantiles. Or you can fit a non-stationary model with, in this case, we're just using simple time covariate, and we can vary our location scale or shape parameter. So just in this case, noting that we're making the location and the scale non-stationary with time. So you can do both those and compare our results. So here we have in gray that split sample analysis, and in blue the covariate analysis. Again, different durations on the x-axis. On the y-axis, the relative quantile change per decade. This does not look dissimilar to what I showed you previously, because I'm looking at a relatively frequent event, a 2-year event. So 2-year events are not particularly rarer than an annual maximum. Where things get interesting is if we look at those rarer quantiles, the 100-year events. Now what you can see is that particularly for the split sample, the median of all those changes across Australia is a lot higher than what was being seen for the frequent events. I would say, let's say if we're looking at the medians, interestingly, the temporal covariate didn't show as greater increases for the rare events, but now we can probably say, look, yeah, 1 hour, 2 hour, up to the 6 hour, the median is still above 0. So we've got stronger evidence that for increases in rare events. So the rarer the extreme rainfall, the more likely it is increasing historically for because of climate change. Now, there's a real interesting application here, right? So because we've fitted a non-stationary GEV with location and scale, and you can see there's a bit of a disconnect here. So what's sort of happening? Well, it turns out that the natural implication here is that actually the shape parameter of the GEV is non-stationary. And so here, this is just a synthetic example to prime this discussion. Here I have a GEV, let's say a historical GEV. And in orange, we've applied a constant change of, say, 7% per degree warming. And the black line, the black dashed line, is the non-stationary estimation, if we were then to fit a GEV to that data that we've shifted up. And so if you just shift up by 7%, well, yes, the quantiles are larger for the rarer events. So, and the quantile estimates are larger, so yes, that increase is larger. But our non-stationary location and scale model will fit the data quite well. But now let's say that the increases for these rarer events are larger than the increases for the frequent events. Well, that's that green curve. So we've shifted our underlying data so that the rare events increase more. And at this point, the non-stationary location and scale model, if we fit it to that data, doesn't actually capture that 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 increase in the tail in the rare events. You can see at the frequent end, it actually drops down below. So it's not capturing that change in skewness and that tilt. And sure enough, if we do make the shape permanent on stationary, then we can fit that variable change. That change that varies with how rare the event is. You can see here. Now, at this point, if you have done extreme value analysis before, I can imagine you might be even tearing your hair out with the suggestion that one fits a non-stationary shape parameter. It is notoriously difficult to estimate the shape parameter, particularly with the short record lengths that we're often dealing with. But this is what climate change is implying, that the shape parameter is actually non-stationary. So I'll show you next how this looks like in practice. So here we've gone with our data from Melbourne in this case, so just one site historically, and fitted all the stationary model to our data, the NS2 model, which we call, that's the one with the location and scale, the NS3 model where all three parameters are allowed to vary with time, and you've got the uncertainties shaded behind. So if we fit a non-stationary model and then we present the quantiles at the end of our record, because climate change has been affecting extreme rainfalls, we can see that the non-stationary models, particularly the short duration, give quantile estimates which are higher than the stationary model, and that's what we would expect. You'll notice that you only see a green, a red line. It's because the red line is plotting on top of the green line. For frequent events, such as a 5-year event, the quantile estimates are pretty similar. But it's for those rare events that using that non-stationary shape parameter makes a difference, and it makes quite a large difference. We're talking instead of a 350 millimeter per hour estimate, something that's 400 millimeters. So you can do it, and it works, and there are methods such as pooling of data that allows you to gives you enough data that you can fit a non-stationary shape parameter. But in this case, we didn't do that. I mean, we're just fitting at one station, and you can see that although the fit maybe was reasonable, the uncertainties are extraordinarily large. You can see that they're going beyond the scales that we have here, the red shading. So user beware, but I think it's a very interesting and finding. So this is not the end of the talk yet, by any means. I'm just summarizing the first line of evidence, and I'll go to the next two in a moment. But for our first line of evidence, I hope that we're all convinced that looking at observations, we can confidently say rainfall increases are greater for shorter durations than longer duration. And the more extreme the rainfall, the greater the increase in the quantile. And this gives evidence that the GEV shape parameter is in fact non-stationary with climate change. But there are questions that remain. We used a time covariate here. So what is the best covariate to use? And what about those longer durations? Rainfall's not increasing. Like, surely we would expect those to increase with climate change as well. So the first bit we'll look at now. What is the best covariate? So the key thing that I need to point out here is that in this work we looked at annual scale covariates. So we're not looking at coincident temperatures or anything like that. We're looking at annual scale covariates, like covariates that would be easy to obtain from climate data, from climate models and the like. So we tested the following 8 covariates: global temperatures, Australian average temperatures, so you can see very strong increasing trends in those historically. Diurnal temperature, which is a proxy for urbanization change. Indian Ocean dipole, IOD, ENSO, these are southern annular mode. These are well-known climate drivers for Australian rainfall. And we also looked at precipitable water anomaly and dew point temperature as well, which dew point temperature is often a proxy measure of how much humidity or moisture is in the atmosphere. So I'm skipping straight to the results. So I'll take you through these. On the y-axis, I have the percentage of sites. So I showed you those 40 sites that we had across Australia. The percentage of sites where the non-stationary model is superior by AIC. And the stars just indicate that by log likelihood statistical test, these results are actually significant. The different colors represent the different covariates that we picked, and here we have all the different duration. So for short duration rainfalls, 6 minutes, what I'm showing here really is that global temperature and time, are probably the most superior covariates. It's probably not that surprising. Global temperatures have been increasing fairly linearly, I guess, with time. But you can see also some of our precipitable water and dew point temperature, they also come out reasonably strong, as in they work very well at a number of sites. But the performance of time and global temperature seems to diminish with increasing duration, and actually these blue bars seem to be the highest in general across the duration. So this implies that maybe precipitable water or dew point temperature is a good covariate. However, this analysis here is only looking at AIC, a statistical measure. But we wanted to look at the trends as well. How do these look if we look at the historical trends? So we did what we did before. We split the sample in two and had that temporal change that I've shown you in grey before, but also just had a look at the trend that you get from start to finish if you use just these covariates. So this is what happens with global temperature. A 5-year event and a 100-year event. So the grey bars behind are just what I showed you in the previous slides. They're just, you split the sample and you have a look at the change between the earlier half of the record and the later half. But the modeled using the covariate is plotted now in this sort of brown shading. And you can see global temperature looks very similar to what the historical observations do in terms of their trend. So in fact, they look fairly similar to what a time covariate would look like. And surprisingly, see, even though in the previous slide, I was suggesting that it doesn't, the AIC is not as great for longer durations. Here you can see that we're capturing the trend for all duration. Now, what's interesting is if we look at the trend in something like precipitable water, the covariate doesn't pick up the trend very well, even though it performs quite well based on AIC. And I would hazard a guess that this is because precipitable water and other covariates like ENSO, they capture the internal variability really well, particularly for longer durations, but they're not capturing that trend. So they capture the year-to-year variability, but they're not capturing those long-term increases. So we can conclude, based on previous literature, so by Catherine Schleff, look, a physically based covariate is probably going to be best if we're interested in projection of extreme rainfalls. And I'll say, based on our work, that global temperature and time are, they're highly correlated at this point in our history. But global temperature does have a physical relationship to how extreme rainfalls might be changing. So it's likely to be the best covariate. Now, I want to just stop and say best. I mean, there are caveats on this work. We're looking at you know, there might be better covariates, for example, if you can really sample very well the drivers of the extreme rainfall event before they're happening. But if you're looking for a large scale covariate, that explains the historical changes that we're seeing, and one that is relatively simple to access numerically, then global temperature does work very well. But, and there's a but, look, we're still struggling to see any increases in the long duration rainfalls with these methodologies that use historical rainfalls. So this is where we come to our third line of evidence, projections. And in this case, in Australia, we have 4 main groups that do regional climate modeling, and we've taken, well, at the time of this work, only one of the groups had their regional climate models output publicly available. So we went with that group. They were a group from Queensland, and they're co-authors on our work and helped us immensely in getting the data. They use a regional climate model called CCAM, but they came up with a 16-member ensemble essentially, and that's what's listed here. So they've used different driving CMIC 6 GCMs, and they've also sometimes used same one, but in different configurations, such as they're not always ocean coupled. For example, the regional climate model is not always ocean coupled. So sometimes they'll use the same GCM, but use a different orientation or a different way of doing their downscaling. Sometimes they use different GCMs, sometimes they use a different ensemble member from those GCMs. But the big picture here is a suite of 16 different ensemble members. So we can evaluate these regional climate models. And again, I'm taking a site in Melbourne. And the reason I'm doing that is because it has quite a long record. And so here we have all the different model ensembles and our observed record. And we're putting our regional climate models to a pretty stringent test here, okay? This regional climate model goes down to 1 hour. The resolution is about, of the model, I should say, is about 10 kilometers, so not convective permitting. So 1 hour rainfalls, our observations, fitting a GEV to our observations at the site, and then taking annual maxima from each of these models and also fitting a GEV. Look, I think this is one of the toughest tests that you could really ask of a regional climate model, because we're asking now, can you simulate a 100-year event in a regional climate model? I would argue, at least in Melbourne, at this site, the answer is probably not. I mean, it looks like we're underestimating extreme rainfalls across all APs. But for 24-hour rainfalls, we're well within the uncertainty bands. And recall, this is just one site. So I'm going to show you these biases. So here's a negative bias, for example, negative bias. I'm going to show you these biases across all the stations, again, aggregated as box plots for each of the models. So a lot going on in these slides. On the y-axis, I have the relative bias. So 0.5 would be a 50% bias. Negative 0.5, 50% underestimation of our extreme rainfalls. This is for a 1 hour duration, so short duration rainfalls, 5-year event, 100-year event in each of our models. So what I showed you on the previous slide for 1 hour duration rainfalls is fairly representative of what's happening across all of Australia. Now, the regional climate model is not capturing the extreme, is not modeling, the rarest of the rarest events. But there is a little bit of a caveat on this. There are a couple of handful of models where actually the 100-year rainfall is represented reasonably well. And I'd say actually very well. And so to me, this is really quite surprising. But it goes to the point that, and most of these models are actually happen to be ocean coupled. Now, whether it's a coincidence or not, I'm not sure. We didn't have enough model runs really to check that. But this is pretty exciting that they're not terrible at actually modeling the 100-year rainfall event. And this is without convection permitting models. And for the 1-day rainfalls, yes, look, of course, there's going to be biases in our models. We are comparing, 10-kilometer grid to a point scale. There's quite a few caveats in what we've done, but I will say that these box plots are overlapping with zero. The thing here is that really I feel confident in saying that for 24-hour rainfalls, we're modeling these rare rainfalls really well in our regional climate model, which as someone who's a statistical hydrologist, I found this a really exciting result. So if we, these biases aside, I think we can say that, okay, the regional climate models do have power in telling us how extreme rainfalls are changing with climate change. So let's have a look at those projections. So here we have the projected quantile change for the far future, so 2071 to 2100, relative to the historical, 1961 to 1990. Again, the median changes of this 15-member ensemble. You can see for the 5-year event, it's not universally projected that extreme rainfalls will increase in Australia, and this goes back to our annual maxima. Recall that we didn't always see positive changes. Indeed, in northern parts of Australia, it does seem that decreases are projected. But as we move to rarer and rarer events, more and more increases are projected to occur. And the reason why I put up these maps is that this is for short duration rainfalls, 1-hour rainfalls. I guess what's interesting is that I have been pulling our records and our stations in all my plots, but it's actually the changes are relatively spatially homogeneous across Australia, despite its variety of climates. So we feel comfortable in pulling the projections together and seeing what they look like. And so the next plot is going to mirror the historical observations in terms of how it looks. So on the y-axis, we'll have the quantile change, x-axis duration. This is projections at the end of the century. Blue is a 5-year event, purple is a 100-year event. So lo and behold, the projections look like our observations in that the rarer the event, the greater the increase, the purple is above the blue, and the longer the duration, the smaller the increase. But here's what separates the projections from the observations. So yes, 5-year events are the 24-hour duration don't seem to be projected to increase, but the 100-year events are. Although these scales probably don't show up particularly well, you can trust me in saying that this is around that Clausius-Clapeyron mark, that median. So if we have actually, from our projections, really strong evidence that our 24-hour rainfalls will indeed increase. And I guess there's the question of why don't we see it in our observations? And I guess particularly for Australia, our internal variability is just so large, we're not capturing the climate change signal for our long durations. But indeed, climate model projections do point to an increase in our 24-hour rainfalls. Now, I like this next figure because it presents this change, but on the x-axis, as I would like to call it. So the quantile change is changing the y-axis, moving vertically up, our extreme rainfalls increasing or decreasing. But this is the change in the AUP, the annual exceedance probability, or change in risk, and it's expressed as a factor. So a factor of 2 would be a 100-year rainfall changing to a 50-year rainfall. The reason why I like this is, as an engineer, I like to probably give like rules of thumb, and sort of checks that one can do on the back of an envelope, as I was taught as a graduate engineer. And here you can see that these apologies, green boxes, the medians are roughly lying around 2. Okay, so the models are projecting by the end of the century, for an SSP 3 7.0, a factor of 2 change in our 100-year rainfalls. So there's a little bit more coming just after this, but in terms of our lines of evidence, we can see that there is a negative bias in our regional climate models for extreme rainfalls. In particular here, I'm talking about non-convective emitting models. But the projected increases for short duration rainfall are less than the observed changes. So that's something that might not have been immediately apparent, but the short duration rainfalls are projected to increase by, and it is superclossus clapeyron. It is in the order of 7 to 10% per degree Celsius, but it's a lot less than what we were seeing in our observations. And that could be to do with this negative bias. But the projected increases for long duration rainfall are greater than those observed changes, maybe arguably with less uncertainty. So we've got different lines of evidence pointing to slightly different things. Now, so this is a flood cross-cutting group, so I do want to just touch upon the implications for flooding in my last couple of slides. This work has fed in one way or another as evidence into what is in Australia's flood guidance. And in our flood guidance in Australia, we stipulate increasing extreme rainfalls per degree warming. Now, for the 1 hour rainfalls, the estimate is 15% per degree warming. You would have noticed that there wasn't that much change in the duration, in the projected increases with duration for the regional climate models. The main line of evidence we have for short duration rainfalls remains historical observations. That's really where this 15% is coming from. But you also saw that for long duration rainfalls, the observations didn't show increases. So their main line of evidence for this 8% increase in 24-hour rainfalls per degree global warming is from our climate models. So we're really using multiple lines of evidence to inform engineers how their extreme rainfalls should be projected with climate change. Now we can apply these in an example setting. So the example setting is dam design that I'll show you. So we are going to pick this 8% per degree global warming. And so if you're interested, this work was published recently, but what the lead researcher here, Michelle, did was she took 18 dams across Australia. Their locations are anonymous, but they are real dams, and used rainfall routing models for each of those dams to route rainfall through and then route it with an increase per degree global warming and look at the changes. And she was looking at dam overtopping floods. So we're talking really rare floods. So we're factoring the 10,000 year event essentially for climate change by 8% per degree global 8% per degree change in temperature. So historical precipitations are factored up. Our rainfall losses in Australia are also factored up. What we mean to say is we have drier soils, so some of that increase in extreme rainfall will be absorbed into the soil. Admittedly, for a 10,000 year event, the antecedent conditions aren't going to matter so much. And then we can route that rainfall excess through our models and look at the change in this case, the return period or the AEP, annual exceedance probability of the dam crest level for different temperature increases. And in the paper, we don't give results for individual dams, and that should obviously protect the dam owners, because in the end, this is research. It's not a design flood estimate. So all the results were grouped together. All these changes in risk were grouped together. And that's what we have here. So what is the shift in risk of our dam crest flood? And what you can see here is, I want to point out, it's not linear. So I've put these little guidelines on. This is a threefold increase and a fivefold increase. For a 3-degree change, the median increase in risk is threefold, like a 100-year event becoming a 33-year event. So a 10,000-year event becoming a 3,000-year event, right? It's quite a large shift in risk. But if you're going for 4 degrees global warming by the end of the century, you're looking at a median of 5.5. These are very large shifts in our risk. And I think this is really, um, I don't know, I mean, I still feel that sea level rise is the canary in the coal mine that we're not talking enough about in terms of climate change. But in terms of flood risk, I really feel this figure hits at home for me that the changes are non-linear. So for every increase in warming, we are getting very large, substantial increases in our risks of flooding with climate change. So I'm very happy to take questions, or we can move on with the meeting. But yeah, I'll stop there and thank you very much for attending.
Great. Thank you, Conrad. Great presentation. A lot of information. That's great. That's nice. Very good. Is there any? Yes, great job. Is there any question for Conrad?
Conrad, thank you for the nice presentation. I have one question. In terms of the comparison to the models, are there events, or is there an opportunity for screening the events? Are all the events likely to be reproduced by them, equally likely to be reproduced, or unequally likely? So is there diversity, you know? So sometimes some types of events are likely to be just poorer captured and others better, even though you looked at magnitudes now. Is there,
Yeah.
I don't know what the diversity is in processes there, and whether that would make a difference if you were to screen them, for example, for those you actually expect to be better reproduced or expect to be less reproduced. Is that
Yeah,
something like
that's
that, or is it too complex to answer that question?
no, it's I want to say it's maybe uh it's beyond what we did here. I mean, we were just
Yeah, no,
doing,
I
like you
understand.
said,
Yeah,
annual
I'm
max.
asking to speculate. Yeah.
Yeah, look, there's currently like I think, yeah, Jason Evans is leading a project under Cordex at the moment in Australia, where what they've done, it's called sub-hourly extreme precipitation. SHEP, always a good acronym. But what they've done is they've looked at the weather stations and the radar and are trying to actually pick out individual events and see if the convective permitting models can actually capture these events. And so they're really going the fine scale, particularly temporally, to see if these events are captured. So the short answer is I don't know, that this research is still sort of underway. But it's a good question because different types of weather events dominate extreme rainfalls in Australia, and so it probably would be, um, you know, if we looked maybe in more detail at how it performed at different parts of Australia, we might have been able to at least infer that, maybe in the tropics, if it's dominated by long durations, maybe it's capturing better there. Whereas, yeah,
Mhm.
so that would have actually been we probably could have actually looked at that in more detail just to at least infer those differences. Yeah, so it's a really good thought. Yeah.
Yeah, because also with your projections from the different models, at least in Europe, I don't know Australia enough, but well enough. But there's also shifts in the type of causal event, no? So, and when it happens and what it produces, and that would be really interesting to understand. So maybe the magnitudes are same, but something else has really changed. So
Yeah,
timing
yeah.
of when it is or something else. So that's what I was wondering.
No, it's a good question. Because at least uh there is some research. I'm gonna just shout out like Kiara Holgate did look at projections of s- certain types of weather events, and was finding that some weather events that lead to flooding are better captured in the climate models than others. And historically in Australia, at least in the south, we are seeing, and I think it's something that maybe is being seen in other parts of the world, shift towards more convective events and less longer duration. It's definitely happening. And so yeah, it's really, like you said, Thurston, it's very important to capture those processes and those shifts in the models if we're going to represent flooding properly in the future. So yeah, so even though that it's happening, but whether it's being captured in the models, I'm not. Yeah, I'm still not sure. Yeah.
Thank you. Thank you.
Thank you.
Great. Any other questions? Good question, Tristan. Any question for Conrad? Conrad, I have a quick question. It seems that you incorporated in ENSO as a covariate to location, scale, and shape parameters, right? If I'm correct.
Yes. Yeah.
So, have you considered, I mean, how my question is statistically how you incorporate it and whether you consider giving lag to ENSO data because I mean hydrology is all about lag, right? So, um, is it?
Yeah.
Mhm.
No, that's a really good question. I mean, I because it was fit linearly, like
Yeah.
all the covariates were fit with the same structure, and no, so yeah, we didn't look at the lag, and yeah, like while because Enzo doesn't have particularly a positive or negative trend in Australia, well, in Australia, uh, the indices that measure Enzo don't have a strong positive or negative trend. So they don't have that, they don't capture that positive association with that's happening with extreme rainfalls in Australia. But having said that, I imagine that if we had used, yeah, it's quite plausible that using a lag or would have, yeah, could improve the performance of Enzo. So I think that's a really, yeah, really, really good point, and yeah, definitely a worthwhile thing to look at.
Great. So I had a student when I was at the University of South Carolina actually look for the last research you showed, and the impact of dam on the floods. So he actually was very creative. And then we work on creating a dam index and then put it as a covariates in the algorithm. So I work with the algorithm part of it, but it wasn't statisticians. He works with him. I mean, he never published it. I mean, he graduated, got kids and job, but we done it 3 years ago. I think that's interesting to see these things that is getting like published, and I would like to see whether it would impact on the time series data or not.
Yeah,
That would be great.
yeah, because I think I hope it's okay in this forum to say this. This uh, a lot of the research that we did at the University of Melbourne was funded by the dam owners around Australia. Like it is very front of mind for dam owners that there is a risk due to climate change, and they want to get ahead of that risk and plan for it, and hence they funded this research. So I think to your point, like research around the risk to dams is yeah, I think is really important in that's if we're talking about critical infrastructure and climate change, that's where most of the risk to life lies. I mean, in dam failure. So yeah, I think it's just really, yeah, really important research, and it is
Yeah.
recognized by the people who own the dams.
Yeah,
Yeah.
great. So you guys get to implement it in Southeast US too, because they get a lot of, over top dams. We have like, I don't know how many dams in South Carolina. It's just thousands of them, and sometimes they get overtop and they have to close them. So that would be also great if you guys could implement it in Southeast US too. So the data is
Yeah.
available for free. So
Oh, right. Okay, yeah. No, that's really yeah. I'll have a look and I might get
yeah,
in touch with you. Yeah, because
yeah,
that'd be really interesting.
yeah, great. All right, thank you. Any other question you guys may have last minute? All right. Thank you, Conrad, again for the great presentation. It was really informative. Thank you. Okay, thank you all. Please continue supporting this initiative. We will have our next meeting on March 6th, 2026. Please join us again, and hopefully you guys enjoy this monthly series. And thank you again, Conrad, and all of you for joining us today. Thank you. Have a
Thank
great
you.
evening. Bye.
Bye.
Bye, guys.